Hello, Sunday, February the 5th. I was eager to start on problem 3. It seems that in question B, part 1 and 2, we have to repeat the work of page 73, and also in 3, and in part C to repeat the work or do the same work as on the next 2 pages, 75 and 76. That's a test that the theory is well understood. So we have to find the Fourier transform of this guy, and we already have from the text that the Fourier transform of this function is given by this. That was the proportional change of variable x using square root t times x instead of x. This is what it gives. So in this question we just have to take care of the translation, and this of course only holds for, or it a priori holds for functions of infinitely differentiable functions of fast decrease. All right. So I believe it was just a question of applying the formula. So the one given in the text is just g of x. So I just apply the formula. And is any reduction possible? It doesn't really seem so. Right, I expected that to be immediate. And there we start on this. Now we have to apply the Poisson formation summation formula, it's called. So let's start. Theta A of t equals the sum, and that's the sum of g up here over all integers n, and that's equal to the sum over the Fourier transform over all integers, and that's actually given here. And for y we take all n. Oh, and that's exactly the other function. So this is just theta A upper index of t we have to take the sum with. Oops, but then evaluated at y so it's a y here. No, not quite. That doesn't really work. Oh, so this is so the t here, that should be 1 divided by t. Yeah. So it's just equal to 1 divided by square root t, theta A of 1 divided by t. And that's what we should prove. All right, so that was the first part. And for the next part, I'll probably start tomorrow. Hello guys, had a lot of domestic chores, cleaning, vacuum cleaning, laundry, buying stuff for lunch and dinner, everything, and Monday night bridge, etc. But now let's try part B, equation 2. I actually prepared a little, copying the idea in the text, and I copied that to the next page. I wrote it here because you could see part 1, which we use here, and then set this outside parenthesis, and t is larger than naught, so we can just write t. And then we apply the summation formula, the definition of theta A. And we subtract unity, 1. So that's the value when n vanishes. So we've got twice the sum from 1 to infinity. And I copied that to the next page. All right. And then we take the modulo of each term in here, that's 1. And they write it explicitly in the text, so let's do that as well. When n is 1, it's 1 minus pi divided by t, 1 minus 4 pi divided by t, plus there we go. And then we set this outside parenthesis. And then in the book, they claim that if t is so small that this is less than 1/2, then this becomes smaller than or equal to, no, smaller than 1 plus 1/2 plus 1/4 plus, and then this should be, so here n is 2, so it should be 1/2 to nth. It should be n minus 1. Here is n1. No, it should be nth. I did convince myself about this while studying the text, but I don't see it right now. So what it does give this part oops, I forgot the number 3 here. The crucial point. And this is obviously smaller than n squared minus 1. Oh, we just need n, even more so. Except, of course, when n is unity, 1, then it just, when n is 1, it gives 0. When n is 2, it should be 1. I'm sorry, this is not totally clear. And maybe I did make it too complicated. So we actually divide by 3 here. That's what I have here. And we just need to show that it's larger than 1. So that's the or larger than n. So that is this guy. And we solve it, the discriminant is 12. So that means there is a positive guy for which it holds, like n equals 2. 4 minus 6 doesn't hold for n equals 2. Now that's strange. It did hold for n equals 2. When n equals 2, it gives... what did I do there? So we put 3 outside. Yeah, it's n minus 1. I should have n minus 1 here. Because here, here it was 1. So I have to change variables. It's n minus 1. All right, then it will hold. See, I had a feeling that what I claimed didn't hold, so I was using the wrong n. There we go. So now I believe it. We can factor this as n plus 1 times n minus 1. And when n is larger than or equal to 2, that holds. The equality holds when it's even. All right, equal. All right. That means that this is smaller. This is smaller than or equal to 2 times t minus 1/2. And this sum gives 2. And then we can let this one be eaten by the constants. So there is some constant. When we are close enough to naught, then we can throw this away just by changing this constant. Instead of pi, then some larger than 1 constant. That's the way I've heard professional mathematicians state it. In the book, it's proven in detail by choosing some t large enough so that is smaller than 4 for t large enough. And then they'll get the same with specific value of c. But we can take any value of c larger than pi, then it will work for t being sufficiently close. That was part 2. Here we have to do the same but with the other function. But, it's that function alone. And it's as t tends to naught. Well, when I sum, there is a point where n equals 1. Let's just take a look at that. Now what do we do? It may be the formula is wrong, or I'm wrong. In either case, time for a coffee break. All right, my coffee is ready. I've had a sip, and while it brewed, I convinced myself that I was right. When t tends to infinity, in both cases, or here we get 1. Oh, and here we get 1 as well. So theta, a both as subscript and superscript, will tend to unity for t tending to infinity. And when it tends to naught, it must simply go as t to minus 1/2. So instead of this, and then we use the reciprocal guy and take 1 divided by square root t outside parenthesis. And we do the same as the other time. From this sum, we discard, now it was subscript, yes, we discard n equals naught, because that gives the unity, and then we double the rest. Now what was it? Plus a squared divided by t and they are all positive, so it's actually equal to so it's 1 plus a squared plus a squared divided, oh, we have done that already, etc. And then we set, yes, what do we set out of parentheses? 1 divided 1 to p minus t. There's no limit to what a can be, is there? Let's just check the problem. I think a could be anything. No, a lies between 1 and naught. There, that's lovely. I missed that. So you can actually make it smaller. We can make this smaller by choosing a equal to naught. Because the square is always larger. And then it's reduced to the formula 2. It's the same we have to do now. All right, that finishes my goal for today, actually. Good morning, February the 8th, 2023. We continue with problem 3. Now everything has been made ready that we should make the Mellin transform of this guy and make the same, use the same trick as they do in the text. I have already written the formula. So theta behaves like 1 divided by square root t as t approaches naught. So we subtract that. And the same, it tends to 1 exponentially. So we subtract that. Then this function is defined for all s even naught. Sure. So we need to show that it's differentiable. And the rule is that the partial differential, so if we have an integral here, for it to be, what should we call it, sigma of s, for that to be differentiable, the partial derivative of phi should be bounded by some integrable function on the interval from a to b. If that's the case, then it's differentiable. And if we have an s naught, and then we can choose a little neighborhood so that the real part doesn't change very much, just becomes like 1 less, and then it's still the integral still exists and are finite, so that means that s is an entire function. The first step is to work on this guy. And what they do in the text is to assume that s is larger than unity so that we can split the integral. And then look at the terms individually. I will be writing a lot of long formulas, I believe. So what I'll do is that I will shut up while writing them and then cut it out after the recording, so that what you'll see is that the final formula suddenly occurs out of nowhere. They're just splitting the integral, and when this is positive, when the exponent of t is positive, then the total is larger than -1, so that the integral exists and just tends to 2 divided by s minus 1, or is equals. Now this we must, of course, or in the book they used the definition of theta, and then we must split this, and that explains why the different series of I don't know which one will occur. And here we have taken n equals 0 twice, so that must be subtracted. Well, time to exchange the sum and the integration. This reminds me of something. I believe it's the gamma function. Oh my god. So I'll just write up the integral we are going to use. To be able to use this, we must add b . And then make the series expansion as well, or the definition. No, you know what, I'll just do b separately. So to add these guys, we have to take the value for n equals 0 out. So we have added this for n going from 1 to infinity, and done the same here with these two, and then when n vanishes we have this result, and it gives the same, so it's twice. And then I made a mistake there, which I've corrected. And then this integral, it shouldn't have occurred. It didn't occur in the book. We'll just leave it for a moment with a question mark. And then I'll make a break while I consider we'll just see how close I am to the result we need to get. Pi to minus gamma. Oh, we are very close. There's still something wrong, and we still have a pole at s equals 0. No, that'll probably cancel with this pole. We'll see about that. Well, of course, there's the pole at 1, but then there is still this integral that I need to figure out what to do with. So that finishes the first run. I think I found the mistake. You probably saw it immediately. This sum has to go from 0 to infinity, as it says here. And I let it go from 1. And then up here we have the n equals 0 we have taken twice, so we have to subtract it. And it's the same here. We have to subtract it. And then it gives a total integral This is a little weird, really. This is an entire function as well, except when a is naught, which is not. All right. So I'll just have to isolate this term, and then we should be able to find out how this function, what this function is like. So I'll just do that on the next page. And this is a meromorphic function with two poles. A simple pole at s equals naught and s equals 1 with residue 2. But gamma s half has poles at, so I would just etc. And that eats this pole. So that means that this function has a simple pole at s equals naught and zeros at s equals -2, -4, -6, etc. All right. Now, what should we show? Extends to a meromorphic functions with a simple pole at s equals 1. Lovely. And then we have to show this equality. And the only way I can see to get about it is to make a change of variable here, simply introducing a new variable u equals 1 divided by t, the reciprocal of t. So I'll pause the video and write the formula we get just doing that. The first we should do was to see what happens to this. dt is minus du squared, and so dt divided by t, then we divide it by t, then that turns out to be minus du divided by u. But we exchange boundaries as well, so that will eat the minus. All right. I have done what I said I would, and a little more. So first we change variables. Then we use the transformation formula. And this gives, and that's in the problem. That's question B, part 1. So this gives square root t times theta A as superscript, and that we put outside parentheses, as well as this guy, leaving this. And here we do the same, and then we take it outside parentheses, leaving this. Now in the book they were so lucky that this turned out just to be S1 of 1 minus S, but we have raised A here, so we have to do it all over again and repeat everything to see what we get. And that will take a while. It's basically repeating what I did here. So I'll stop recording and write that, and then we'll see what I've got. I have done what I said I would, and a little more. We use the definition of theta A, which we have here. And we split up the sum for positive and negative n, and take out when n is naught. Where did I do that? The integral from 1 to infinity. Oh, that's what I forgot probably. And then here, what did I do here? Oh yeah, I took them separately. And this is the same parenthesis, and then of t to minus 1/2. And unity is because when we set n equal to naught, we get unity here. So that's integral. And then it appears that I forgot n equals naught here. Theta A when n is naught. That gives unity. So that is eaten by unity here. All right. So that's it. And then these two, I have exchanged sum and integration as well. And then these two terms add an integral from naught to infinity. And then this integral, when the real part of S lies between naught and unity, both can be computed to give this. And then we use the same formula. We compute the integral from naught to infinity, and that gives this guy to minus s halves, and pi to minus s halves, and that's pi to minus f half gamma s halves times this sum, which is exactly zeta of a point s and zeta of 1 minus s here. No, 1 minus a point s. And then this, that's what we have already done. So now we are over here. So we need to check out theta A superscript when n is naught. Does that give unity? Yes, that was what it did. All right. Then I forget the gamma function here. I forgot the gamma function. It should be gamma of 1s divided by 2, I think. Yes. So here we should have gamma of 1 minus s halves. So we should have gamma of 1 minus s halves plus the two guys. And now we just need to compute with what we've already got. So S1 of s gives this, and these two terms should be the same. They have opposite sign. Unfortunate. How on earth could that happen? And then this term shouldn't have occurred actually, or I'm missing it over here on the next page. Otherwise, we are very close to doing what I was told to do. So pi to minus 1 divided by, oops. So I simply made a number of sign errors, and then it turns out that this guy shouldn't be there, or should be on the second page. I don't think I might just have time to find the error and then show you where it is and correct the result. But that was about as close as I could get today. Hi there. This is now the next day, February the 9th. What I have done hitherto looks very much like a major or larger computation where one uses some sheets of paper and finally gets a result which is wrong. And then what one has to do is to repeat the computation, and then eventually it will start converging to the right result. I showed you the first time I went through it, then I have done it one more time and then written it on the whiteboard here. So I think I have the right result now, third time through. It's not too bad. And then I'll just explain it to you. Already in part question B, point 2, point 3, I made a mistake. So we'll just look at that. That's what we have here. So the definition of theta sub A, which we have here, shows clearly that as t tends to infinity, it drops off exponentially. There is a little technique for an undergraduate to show that, but we'll leave that. I actually thought I did those details wrong during the first recording. Never mind. So that drops off exponentially, and theta super A, when n is naught, we get unity. Otherwise, it drops off exponentially. That's what we have here. And then we use the transformation formula to see what happens when t tends to naught from above. And should we call it the reflection formula in part I here? Gives this, and then we use the the bound here with C1, and then by adjusting it slightly downwards we can eat this 1 divided by square root t. And of course that's also the professional way of doing it. The undergraduate have to make some details here. And starting with this bound and substituting t to t minus first, we get this, which leads to this. So that's part B. And that means that when we define our entire function, we must, with sub A, we must introduce a correction term for the integration from 0 to 1, or whatever you like, by the way, and we don't need that going to infinity. So we've started on part C now. When the real part of s is larger than 1, we can split this integral and do them each by itself. And using the definition, now what did I do here? Oh, then I collected the integral here from 0 to infinity. And introduced the definition of theta sub A. And then we apply our integral here, we know the result, and then we get this, and going from now where are we going to from n plus a to s? Yeah, we must add from 0 to infinity to get the zeta function, and then we have from 1 to infinity left of the negative numbers. And then it turned out that actually raising this negative number to a complex exponential, that's multi-valued, not so nice. The remedy is to split already up here. So that we first take the positive, which we already have here, and then the negative ones. So n, it's minus n up here, and then we just change sign of what needs to be squared. Now we can do it again. And then in this sum, where we have n minus a going n from 1 to 0, then we can just substitute it with a new 1 in mark, so that it's n is in mark plus 1. And this can be read exactly as the zeta function of 1 minus a point s. So that's what we get. This is an entire function for the usual reasons, or reason that it's, I have explained that. So we isolate this guy and have s minus something having a pole at s equals 0 divided by this constant. This one has a pole at a simple pole at s equals 0 as well. So that means that that pole can be removed. So this is actually an entire function. How come I write it has a pole at 1? Oh yeah, and this doesn't. So it has a pole at 1. I was already remembering the next part. And then gamma has zeros at negative integers, so that means that this function has zeros at 0, -2, -4, etc. Oh yeah, and at 0, of course. So that was the first part of question C. For the next one, we write up the definition of S1, and then we make the usual transformation. So this becomes from 1 to infinity, and this from 0 to unity. And then we use the transformation formula. And here we split again, first taking the positive part of theta super A, and then the negative part, so it's minus n, and this gives the same, of course, and use our, we know the integral, so the constant term comes outside, and then we have this constant times n to 1 minus s plus then this constant, and then n to 1 minus s, and plus this, of course, again, which we have computed here. This is exactly L of 1 minus s. This is a little more complicated. The first time I wrote it up, I just wrote L of minus a 0.1 minus s, but we want this to be a number between 0 and 1. But this is periodic with a period of 1, so we can just add 1 to minus a. So that's the L function, the relevant L function. Now we do the same, isolate this guy. So we subtract this and divide by the constant. And then we can see that the pole at s equals 1, this has a pole at s equals 1, as does this, a simple pole. So they cancel. That means that we have an entire function. This has zeros at 3, 5, no, poles at s equals 3, and of course 1, but 3, 5, 7, etc. So this is an entire function with zeros at -2, -4, -6. And then the formula that we had to show in the exercise on the problem, it follows directly from the two expressions we have of S1 of S. Whoa, that was part A. Turns out to be rather complicated. And we'll see when I'll be able to start on the next problem. But having learned from the experience here, I will read the problem very carefully before starting on the computations, because some of the mistakes I made here was because I simply hadn't read the problem really thoroughly.